Hi everyone. So last time we covered a very simple example of likelihood maximization, and that was the example of looking at a Brownian particle diffusing and basically asking the question, from the localizations can I deduce what the diffusion coefficient is? And then we talked about a really interesting example or generalization where we said, well, suppose that we had measurement error. In that particular case, what would that lead to? And we know that would, from measurement error, we would conclude that the apparent diffusion coefficient is actually larger. So what I'd like to do today is sort of briefly, cover one likelihood maximization technique, and then eventually talk about sort of how to treat measurement noise. So likelihood maximization is generally an optimization problem. And while this class is not a course on optimization, I feel I do need to say a thing or two about optimization. If our likelihood, for example, let's call this theta, were to look something like this, and the goal of optimization, for instance, could be to identify the maximum of the likelihood. One challenge, as we've pointed out, is that oftentimes, for the types of problems that we're solving, the likelihoods themselves can be multimodal. And in fact, this is only the case of one dimension. In practice, these modes can exist in multiple different dimensions. And so then it becomes a very difficult problem to sort of identify a global optimum. It even becomes a difficult interpretational problem. So not only a computational problem, but an interpretational problem in asking, well, what do the maxima or the various maxima really mean? And then eventually, mathematically, we will even find that a lot of problems have these inherent symmetries where you can have multiple different maxima for mathematical reasons, not physical reasons. Something called label switching that we may touch upon later on. But be that as it may, maybe we can discuss sort of one optimization technique and then sort of leave the interested student or listener to take a look at some of the other ones discussed. And the very first one is Newton-Raphson optimization. So the way Newton-Raphson optimization works is essentially by considering the gradient. And in this particular case, typically speaking, we consider the log likelihood, not the likelihood itself, because the likelihood itself may be extremely small. So we're typically trying to maximize the log likelihood. And numerically, we'd like to be able to find a value of the log likelihood that is approximately equal to 0. It won't precisely be equal to 0 for numerical reasons. Well, one possible strategy is to start by considering a theta old value, and then eventually moving on to something theta nu, where the gradient of the log likelihood is approximately equal to 0. So, in some sense, we think of expanding our log likelihood around some theta old, where the gradient of the log likelihood is not 0, and consider a perturbation upon that. And that perturbation we'll call h. So the idea here is that theta old plus h equals theta nu, and theta nu is the value at which the gradient of the log likelihood is approximately equal to 0. So if that's true, then we can take this and expand it around h. The first term will be the constant term, where h is 0. The second term, or the first Taylor term, is the derivative of the derivative. So in fact, it's a second derivative. So let's go ahead and write it down. I'll define some matrix called a Hessian in just 1 second, but it's going to be a matrix of second derivatives. So I'm going to have h log p of w1 to n conditioned on theta. And then finally my h transpose. So in this particular case, I'm imagining a multi-dimensional optimization. I'm not just taking the derivative with respect to one parameter like the diffusion coefficient. I'm actually taking a gradient with respect to a lot of different parameters and setting those equal to 0. So that ultimately gives me sort of a set of equations, a set of linear equations to solve for the various theta. Okay, so we just need to define at this point what this h is. And of course, we're saying that this, at this point, is approximately equal to 0. So let's go ahead and define our h. And before that, let's define also our gradient. So our gradient was dd theta 1, dd theta 2, all the way to dd theta sub k, assuming that we have k parameters. And the h is going to be a matrix of second derivatives, d squared d theta 1 squared, d squared d theta 2 squared, and so on and so forth. In the off diagonals, we will have our mixed derivatives, d theta 1, d theta 2, d theta 2, d theta 1, and so on and so forth. Now, the example we had looked at earlier in terms of learning the diffusion coefficient, that was pretty easy. It was in one dimension. So in some sense, rather than having a gradient, we would have had just a simple first derivative. Okay, so from the equation we wrote down just earlier, namely that 0 was approximately equal to the gradient log p, I'm not going to write all of its arguments, plus h log p times h transpose. Transpose just to make sure that we're keeping all of the right dimensions. We would like this to be a column vector. And knowing that h is theta nu minus theta old, then we can actually solve for theta nu in terms of theta old. And what that gives us is a theta nu, approximately equal to theta old minus gradient log p transpose multiplied by the Hessian log p inverse, right? I've essentially just solved this equation for theta nu. Now, algorithmically, the way it's traditionally implemented is as follows. So this is an algorithmic implementation of Newton-Raphson. And in this particular case, you start with your likelihood, or more precisely the log. You try to pre-compute an analytic formula for the likelihood as well. And you should probably start off with some theta old, some kind of initial condition. And if all that's true, then basically the algorithm itself is rather simple. You essentially solve the linear set of equations h multiplied by h log p theta old equals negative gradient log p theta old and then ultimately set theta nu equal to your old theta plus the h. Here I kind of use shorthand notation. In principle, I could have written w and then conditioned on theta old, but I'm just abbreviating my notation a little bit. And that is it. So this, I should say, is a bullet point. It's not a minus sign, so maybe I can do something like this. This here is genuinely a minus sign. So this is one method of going about solving for a likelihood. Again, it's not going to be completely general because it'll depend on the likelihood, sort of, you finding that global maximum. And generally speaking, as we start working our way toward Bayesian logic, we'd like to be able to sample from distributions over parameters and not just sort of optimize them. So shortly, we will be exploring the following object. And this object is different from the likelihood. It has a name, and it's called a posterior. And this object tells me about how my parameters are distributed, or what possible values for the parameters are warranted by the data as I observe it. This is quite different from the likelihood, which is a restatement. This is a likelihood of what is the probability of observing that data given the model that I have assumed. And again, in maximum likelihood, you try to maximize the likelihood with respect to theta, the model parameters, in order to find the model parameters that are more likely to explain the data. But in doing so, you don't really learn about what model parameters are acceptable given the data. You find one typically called point estimate. When you consider posteriors, this more general object that we're working our way toward, instead you start asking questions about, as we mentioned, sort of how the parameters are distributed. So we will be working our way towards sampling, which is a much more sort of general way of solving the problems than by simple optimization, but haven't gotten there yet. So the next step at this point is now to introduce sort of how to treat measurement noise in likelihoods. Thank you.